All right, so let's look at some example problems similar to the ones that you'll be doing in your problem set. So we've got a contour map, and just so that we can see what's going on, these are my contour line, or my z values rather, and I'll look at we're looking at point R, and we want to find f sub x and f sub y, so these are the partial derivative in the x direction and the y direction. So if we go to R, and we increase just in the x direction, what we notice is that we started at this starting point was 19, and then the first contour line that we hit is 18. So as we went, so f sub x is going to be less than 0, because as we move to the right, z decreases. And f sub y, well, at the point R, if I go up, same thing. As I move up, the z decreases. And when I say z decreases, what I'm saying is that looking at this value, that contour is 19, and then we hit 18. So our z value is going down. It says using the difference quotients, estimate the partial derivative of x at 5,3 and the partial derivative of y at 5,3. So let's find an expression for f sub x, or the partial derivative with respect to x. What we can do is we can think about this function. We could think about our function as 1 over y plus 2 times x squared. And if we're just changing x, then this 1 over y plus 2 is a constant. So the constant just stays there. And then we take the derivative of x squared, which is 2x. Well, now we plug in the points. And when I plug in the points, I'm going to get 1 over 3 plus 2 times 2 times 5, which equals 2. So that's the partial derivative with respect to x at this point. Well, what about y? Find the partial derivative with respect to y. Well, similarly, what we can do is think, again, about my function. But now I'm going to write it as x squared times y plus 2 to the negative 1. And in this case, x squared is a constant because I'm only changing y. So the partial derivative with respect to y would be x squared times negative 1 times y plus 2 to the negative 2 times the derivative of the inside, which is just 1. So this equals negative x squared over y plus 2 squared. And then if I plug in the points, 5, 3, we have negative 5 squared over 3 plus 2 squared, which equals negative 1. All right, so now we have a table, and what it's looking at is the temperature that's adjusted for wind chill. So we've got temperature as a function of or sort of the felt temperature as a function of wind speed, and the actual outside temperature. And what we want to do is estimate the partial derivative with respect to temperature at the 0.55. So we go to the 0.55, 5, and we want to just change, we want to see what happens when we just change temperature. So if we just change temperature, when our, let's see, the change in our function is going from negative 5 to 1, so it increases by 6. When the change in my temperature goes from 5 to 10, which is 5. So the partial derivative at that point equals 1.2. And what that means, that 1.2, says that if, so the way to interpret that is when I'm at a temperature of 5 with a wind speed of 5, if the actual temperature were to go up by a little bit, by 1, if the actual temperature were to go up by 1, we would feel like it goes up by 1.2. Okay, more partial derivatives. Here's a contour diagram, and we want to know, is f of x positive or negative? So what we can do is just think about going to some point here, any point, and we're going to only change, so we're at this point our y value, or sorry, our z value is 2, and if I just change x, because I'm looking for partial derivative with respect to x, if I just change x, I'm jumping from 2 to 6. Well, let's just choose another random point. If I'm here at 6 and I just change x, I jump from 6 to 10. So partial derivative is positive. All right, here we have a saddle, and we've looked at these graphs before. So it says, what's the sign of the partial derivative with respect to x at 0, 11? And so the idea is we're just, the partial derivative with respect to x is we're just changing our x value, so in this direction. So when we change x, we see that our z value is going down, so the partial derivative is less than 0. Whereas in the y direction, if I just change in the y direction, my z value goes up. So fy at that point is greater than 0. Okay, now this is the last problem. We want to find the partial derivatives with respect to x and respect to y. So let's do f partial x. So in here, we're going to treat all of our y values as constants. So when we treat all of those y values as constants, we're going to get 2y cubed, because that's the constant in here, times the derivative with respect to the derivative of x, so 2x. Plus 3y squared times the derivative of x with respect to x, which is 1. And then minus 8, so now taking the derivative of this here, minus 18x. So again, we treated each of these y values as constants. And so the only thing we were taking the derivative of were the x values. So the derivative of x squared here was 2x. The derivative of x was 1. The derivative of x squared was 2x, which turned into 18. Okay, what about partial derivative with respect to y? Well, now, since we're dealing with y, we're going to treat each of these x's as constants. So the partial derivative with respect to y will equal 2x squared times 3y squared plus 3x times 2y. And then, since there's no y's there, even though there's an x, we're treating this as a constant because we're thinking about just changing our y. So we get minus 0. And so these are problems similar to the ones you'll be doing in the next problem set.